Alright, you guys, this one is probability rules. This one directly follows the one probability model, so make sure you watch that one first. Um, okay, so rules on probability, and I'm going to write it P of A right there. It just means probability of A, okay? Probability of A is between 0 and 1. It could be 0, it could be 1, but it's nothing outside of that. It's usually a fraction. I've noticed your book represents it as a decimal, so just take top number and divide it by bottom number to change it to a decimal. Okay, and this is how you get your probability. Your fraction is the number of favorable outcomes, and the bottom number is your total number of outcomes. I'll explain some more as we get into some examples. So S is the sample space, and the probability of S equals 1 because it's 100% in your sample space. And the complement of A, this is our complement rule, you guys, written A with a C up here. That means A, the complement of A. And it's equal to 1 minus, remember the sample space is 1, so 1 minus the probability of A. Okay, so they're complements of each other. They take up the whole sample space. All right, and notice probability of A is also 1 minus probability of its complement of A. All right, so if A and B have no no outcomes in common, then here's a Venn diagram that represents that. Okay, notice they don't have anything in common right here, and here's my sample space right there. All right, and then they are mutually exclusive with each other, and we use the addition rule. If they're mutually exclusive, then the probability of A or B means the probability of A plus B. Typically in math, or means plus. All right. Here's a Venn diagram showing the sample space and A and its complement. Okay. So here's my sample space right here, and then the division for my A and my complement. So there's a Venn diagram showing the sample space, and notice A and its complement take up the whole sample space right there. Okay, and then this says union right here. So A union its complement is the whole sample space right there, and then and union typically means or. And this is our intersection, our symbol for intersection, so an upside down U. So A intersection with C this is called the empty set, you guys. And intersection typically means and so they don't overlap. There's no overlapping with them. So this just means the empty set. And this is set notation. These brackets are called set notation. So there's nothing in between them. It's empty. So this would be the empty set. So I think it's easier just to write it like this. This does not mean 0. It means the empty set. Okay. So marital status of young women. And this is example 6.8 on page 344. So draw a woman at age 25 to 34 years old at random and record her marital status. At random just means that everybody gets equal chance to be picked. That is, if we choose an SRS of size 1, everybody has the same chance of getting picked. Okay, the probability of a marital status is just a proportion of all women aged 25 to 34 who have that status. So if we draw many women, then this proportion is what they would get. I don't know where these numbers came from, but this is what they got. Okay, so marital status, never been married, which would be almost 30%. Married, 62%. Widowed. Now the reason why this is so low, you guys, is because these gals are young, so they're not going to be widowed at a young age. I suspect when they get much older, this number would get higher, and this number over here would get much lower. Okay, so we're going to work with these numbers right here. All right, so I just moved it up right there. Each probability is between 0 and 1, and the probabilities add up to 1 because it's the outcome of the whole sample space. I bet some of you guys are going to add those up to check to see if it equals 1. I would. Probability that a woman we draw is not married, we can use by the complement rule, but check this out. Not married, you guys, it would count for never married, or widowed, or divorced. If you added all those up, you get the same as doing this right here. The complement rule is just take subtract off the people that are married. It's quicker just to do it that way. And 1 minus 0.622 is about, well, it's 37.8%. Okay, you get the same thing if you add it up. Never been married with widowed and divorced, you'd get 37.8% as well. Okay, so that means if 62% were married, then the remaining 37.8% are not married. And never married and divorced are disjoint events because no women can be married or divorced at the same time. Okay, so you can use the addition rule on that because they're disjoint events. The probability of never married or divorced is the same as the probability of never married plus the probability of divorce. And you just take those numbers up above and you get about 37.3% or 0.373. Okay, let's see. So here's some dice probabilities. And so this is that we're going to use the same example we did in the last lesson, you guys. So from that figure, we get these 36 different outcomes. Okay, so that would be the bottom number, by the way, 36. And so, okay, I just moved it up, made it a little bit smaller. So casino dice are carefully made. Their spots are not hollowed out because it would give the faces different weights and different likelihoods to be rolled. So what they do is they fill those things with white plastic of the same density as the colored plastic of the body, so they weigh the same. So they all have equal chances to be coming up. So each chance has 1 out of 36. So this is 1 over 36 probability. So if I wanted to roll, this pair right here has 1 out of 36 chances right there. Okay. So gamblers are often interested in the sum of the pips of the up faces. That just means the numbers on the sides up. So what's the probability of rolling a 5? Because the event of rolling a 5, remember from the last lesson, there was 4 ways to roll a 5. So the probability would be 4 out of 36 right here. So there's 4 ways to roll a 5 out of 36. This is favorable outcome right here, 4. And this is total amount of outcomes. I would reduce that to 1/9, you guys. I like fractions better, but they changed it to a decimal, 4 divided by 36, but it's 1/9. It's the same as 0.111. Okay, so what's the probability of rolling a 7? Okay, there was, if you go back there, let's see if I can find it. There's 6 ways to roll a 7 in there. So if you looked in there, there's 6 out of 36. So 6 out of 36 would be 1/6. I'd rather have 1/6, but they changed it to a decimal to 0.167. Okay, so when you're looking at your answers in the back, you just change it. Okay, this is something I didn't know about until I started reading out of this book, Benford's Law, and this is example 610 on 345 and 346. It deals with taxes. So fake numbers in tax returns, payments, records, invoices, expense accounts, and many other settings often display patterns that aren't present in legitimate records. Some patterns, like too many round numbers, are obvious and easily avoided by a clever crook. Others are more subtle. It is a striking fact that the first digit of numbers in legitimate records often follow this distribution that's known as Benford's Law. And so I wasn't aware of this, you guys. So this is how they catch tax fraud people. The first digit, you guys, the probability that the first digit is a 1 is 0.301. The probability that the first digit is a 2, look, it keeps going down. This is the first digit. The probability that the first digit is a 9 is 4.6%. So that's how IRS people catch people is by this right here. So Benford's Law usually applies to the first digit of the size of similar quantities, such as invoices, expense accounts, claims, and county populations. Investigators can detect fraud by comparing these probabilities with the first digit in records, such as the invoices paid by businesses. So consider the event A, that it's the first digit is 1. Okay, so that would be the probability right there. Consider event B, that the first digit is 6 or greater. Okay, 6 or greater would be this one plus this one plus this one plus this one. Okay, so from the tables up there, we get what I just said right there. So here's the probability of event A, and then here's the probability of event B. Okay, all right, so note that the probability of B is not the same as the probability of a random digit that's greater than 6. I should have left this out. Because it says the first digit is 6 or greater. Can you see that does not mean is greater than 6 on that, you guys? So it's different. So just different meaning right there. The probability that the first digit is anything other than a 1, you can use your complement rule, because you know the probability of it being 1 is 0.301, so anything other than 1 would be the complement, so you do 1 minus that. Complement's a good trick, you guys. It's just a shortcut to figure that out. Okay, so events A and B are disjoint events. So the probability that the first digit is either a 1 or is 6 or greater, you can use your addition rule. Okay, remember we got this by adding all those 6 or greater, and here's the probability that event A is a 1, so you get about 52.3%. Okay, be careful to apply the addition rule only accounts for, you can only do the addition rule to disjoint events. So check that the probability of event C that the first digit is odd. Look, here's the event C that the first digit is odd. You can get a 1, 3, 5, 7, or 9. Okay, so that's the probability that it's odd. All right, easy enough. The probability of B or C, now check this out. These guys are not disjoint because remember B was 6 or greater. Well, 6 or greater and event C was odds. They both include outcomes 7 and 9, so they're not disjoint. So you gotta add them up together, you guys. So probability of 1, 3, 5, 6, 7, 8, 9. Okay, because you can't just add probability of event B with probability of event C. You have to add them up separately right here. Okay, because they both share 7s and 9s. So random digits, so this is example 611 on page 347. Okay, you might think that the first digits are distributed at random among the digits 1 through 8, so we're outside, we're not doing Bedford's law anymore, you guys. So the 9 possible outcomes are on just random digits, you guys, are 1, 2, 3, 4, 5, 6, 7, 8, 9. Now it's not, zero's not included because it didn't have 0 through 9 right here, just it said 1 through 9. So there's 9 possible outcomes. So if there's 9 possible outcomes, then each probability of getting a 1 would be 1/9, and a 2 would be 1/9, and a 3, the probability of getting a 3 is 1/9, and the probability of pulling any digit is 1/9 right there. You guys with me? Yes. Okay, so the probability of event B that a randomly chosen first digit is 6 or greater. Okay, this is not Benford's law anymore. This is just regular digits, you guys. So 6 or greater would be 1/9 plus 1/9 plus 1/9 plus 1/9, which would get me 4/9, which is 0.444. And they just want you to compare that 0.444 with what we got in Benford's law. And I should have copied and pasted that, but I didn't. So whatever we got with in Benford's law would have been different. So compare this with Benford's law, and a crook who fakes data by using random digits will end up with too many first digits, 6 or greater, and too fewer ones, and they will probably be arrested.